Okay, so I hope everybody is having a good day. We're trying something a little bit different, obviously. Um, we were at a point where we needed to do some notes and some discussion, but of course I was scheduled to do PD today, so we're going to try to see if we can communicate via video this time. And we have a little bit of a shadow going on, trying to figure out what that is at the end, bottom of the screen, but hopefully um, looks like it's the shadow of the camera. Hopefully it won't be too annoying. All right, so this is the do now that you were faced with today when you took your packets out of the, or I guess from the substitute really. So let's label the parts of the atom. Hopefully you have these all correct because you already know the parts of the atom. So this right here, this circle or this little sphere in here, there is no other indication that there's a charge or anything like that. So this would be your neutron. Over here, this circle seems to have a plus sign in the middle. That means that it must be a positively charged particle. So therefore, that's the proton. Together, it probably would be better if this was drawn somewhat like this. Those two structures are located inside the nucleus. And this structure down here has a negative sign inside of it, and so therefore it is an electron. Now the only thing this diagram doesn't ask you to label are these guys out here, and you really can call these a couple of things. I'm not picky on what you call them, so whatever you're used to calling them is fine. Sometimes you'll hear people refer to them as orbitals. You can also call them shells, which is, it sounds like what you guys are used to calling them. And sometimes you can call them energy levels. That's probably what you want to get most accustomed to calling them because you will be calling them that in chemistry, I'm sure. And if you want to go kind of old school, they were called clouds at one time. They're not really called clouds anymore because that theory of how they move around is a little bit old. They don't really move like that anymore. All right, so let's move into the packet. Okay, I'm sorry they're not in pre-color like they would have been if we were actually using the LCD and the projector, but at least I'm writing in color. Maybe that's a little bit more attractive. Again, this is just to review that the general information about atoms, you know that atoms are the smallest particle of matter. Okay. We talked about what the protons and the neutrons and where they are inside the nucleus. One thing we better clear up is maybe the abbreviations I use, just so that you get used to them. Protons are written as a P with a plus sign. Neutrons are written as an N with an O or a 0, I guess. And electrons are an E with a negative sign. Okay, let's go into some of the more difficult vocab. The atomic number is a number that is specific to that element. And we probably should have defined elements as being a substance that is all the same type of atom, but I think you kind of came to us with that one. So, because it's specific to that element, we know that it can only belong to that, so it can also distinguish something else for us. So the atomic number is equal to the number of protons. In a neutral atom, meaning there's no charge, we'll get to that in a second when there is a charge, the atomic number is also equal to the number of electrons. Okay, atomic mass and mass number are a little bit different, and we're going to make some stipulations to that to you today. So the atomic mass, probably you've learned, is equal to the mass of the protons, the neutrons, and the electrons. However, what we really know the atomic mass to be is the average of all of the masses of the isotopes of the same element. So it's kind of hard to talk about the atomic mass when we haven't talked about what an isotope is yet. But we kind of have to keep them separate because I want to make sure that you're doing this logically. So if you want to think of it instead of isotopes as just types of the same element, then you can do that. So if I take all the different types of carbon that are out there, which again, if we're talking about isotopes, things like carbon-14, carbon-13, carbon-12, which is your regular, naturally most abundant type of carbon, and I add up all of those masses together and divide them by whatever the number of types there are, that's how I'm getting an atomic mass. It used to be said that, yes, it's the number of protons, it's the number of neutrons, and it's the number of electrons. And there even have been some teachers who may have told you that, you know, all those decimals that are at the end of the atomic mass, that's really what the electrons weigh. And that's why they put them on there. Not exactly the case. It is actually an average of all the different masses of all the different isotopes. But electrons are pretty negligible in how much mass they're adding to the atoms anyway. So yeah, technically they might just be a certain amount of decimals, but there are some who say that they're not even that large. The amount decimal wise, or the amount or the number of, you know, whatever the decimals are supposed to be equaling is even too much for what the electrons would weigh. And in all honesty, could you really weigh an electron to begin with? Electrons are constantly moving around the nucleus of the atom, so could you pin one down long enough to actually take the mass of it? Probably not. So that's not at all what those decimals are. Okay, so now let's do the differentiation between the atomic mass and the mass number. Mass number is equal to the number of protons plus the number of neutrons. Forgot my little plus sign. And usually what we're using the mass number for is to find the number of neutrons. So typically you'll be given the mass number in some way, shape, or form. If you're not given the mass number in a formula, so for example, we'll use S as a symbol there, just meaning symbol, okay? You're usually given the mass number up here and the atomic number down here. And later on we'll see that if there's a number here with either a plus or a minus, that's the charge. And I'll straighten all this out for you, why we're pulling this information from here in these things. I'm sure you've seen a chart that has this kind of information in it. So the reason why we set this up, and sometimes you'll see this as, people will refer to this as the isotope symbol, or the way to symbolize an isotope. The reason why I'm pointing this out to you now is because in order to find the number of neutrons, we're going to take the mass number and subtract the number of protons, and that will give us our neutrons. And what's nice about this symbolization is the mass number sits on top, and your atomic number, your number of protons, sits at the bottom, and you have a very easy peasy little math problem sitting there waiting for you. Especially if you're like me and tend to have brain freeze and can't do subtraction or addition in your head without a calculator. It's terrible. Anyhow, so that's how basically what we most of the time use mass number for. So let's go down and talk about ions. Hopefully, from what I'm sensing from other classes who I've already done these notes with, most of you know that ions are charged atoms. Most of you remember that there are two types. We could have positively charged atoms, or we could have negatively charged atoms. And each of them has a name. A positively charged atom is a cation. And a negatively charged ion is an anion. The easiest thing for me to remember which one is which is that the cation actually has the positive sign, also known as the letter T, in the name. That's just one way to keep them straight. Okay, so an example of a cation would be something like sodium +1. An example of a negatively charged anion would be something like chlorine -1. But how do I get charged atoms? Most of the time, I'm starting with neutral atoms. So we need to know where these are resulting from. And you get ions from the dissociation or the breaking apart of an ionic compound. That does say compound down there. Sorry about that, guys. At least there's no house elf in my board here. Okay, last thing I want to clear up, just definition-wise and kind of general information-wise, is isotopes. Isotopes are atoms of the same element with a different number of neutrons. Oh, I know one thing we forgot, and it's going to become important in a second when I ask you about the difference between isotopes and ions. I'm going to write it in a different color because I did forget it. So, let's see. Which was this one? One thing we forgot when we were talking about ions is how they become charged. And how do I get, excuse me, and how do I get a positive ion versus a negative ion? So we didn't define here how we do this, and we better do that. So in a positively charged cation, I'm going to lose electrons. And in a negatively charged anion, I'm going to gain electrons. So in an isotope, I'm not doing anything with my electrons. I'm also not doing anything with my protons. That's important. And that should really go up here in atomic number in a different color. You cannot change the number of protons. If you do, you change the element. And we'll go back to that in a second. So let's finish up isotopes. Most of the time when we're talking about isotopes, at least the ones that are helpful to us in biology, we're talking about radioactive isotopes that we use for diagnosis or dating organic material. So for example, carbon-14, I think you all remember, is for carbon-14 dating, where we can take the radioactive half-life of carbon-14, and be able to count back how many years old something is by looking at the percentage of carbon-14 that's present in the mass of that object. Other ones you may be less familiar with, things like barium or iodine. If you've had MRIs or CAT scans and they ask you or tell you that you have to have it with contrast, if you have an MRI or a CAT scan and they require a contrast dye, then it's probably iodine that they're putting in you. And they inject it in you, kind of gives you this warm feeling going throughout all of your body. And as they're taking the picture, the CAT scan or the MRI image, they're seeing the flow of the iodine through the different parts of your body that they're imaging. Barium is used in x-rays. If you've ever had to go for what's called a swallow study or something like that, an upper GI series, or if your parents or your grandparents or aunts or uncles or hopefully older people and not you yourself have any kind of gastrointestinal issues, it's barium that they're probably using as they're taking the x-rays or the X-ray video nowadays of the material of the radioactive barium moving through your GI tract. Okay, I think I've said what I wanted to say about these guys in general. So let's see about moving on to the next page. Which would be right here. I just want to do a quick review with you guys about drawing Bohr models and drawing Lewis structures. To model the electrons that are surrounding the nucleus, we have two different ways. I personally prefer the Lewis structure, and that's probably the most common way from now on that you're going to demonstrate. But you should know how to draw a Bohr model because there are reasons why we teach you the Bohr model first. So when you draw the Bohr model of an atom, you're usually just drawing the electrons that are surrounding it. Sometimes you'll have teachers who say, well, just put the symbol inside the nucleus. Sometimes you'll have teachers who tell you to, put the protons and the neutrons in there. Either way you cut it, it's basically representing the same thing. So I'm going to use lithium as our example for Bohr model and for Lewis structure. And you all hopefully have your periodic tables. If you want to take a second or two to pull them out, that's fine. I'm just going to write that we're going to use lithium as our example. And our symbol for lithium is Li, if you're trying to locate it on the periodic table. Again, you might want your periodic table out, so you want to get that. That's fine. Okay, so find lithium on the periodic table, and what you should see is that lithium lives in column 1, and his atomic number is 3. And since his atomic number is 3, he has 3 protons in his nucleus. In the first shell, I think you'll remember this, you can put 2 electrons. And then in the shells after that, for our purposes, you can put up to 8. Next year in chemistry, you're going to learn that that's not necessarily the case. And once we get past that third shell, it gets kind of rocky. And we have some electrons and some orbitals doing some crossing over. And it just gets a little bit more confusing. Something to look forward to. Chemistry being more confusing than biology. So in our first shell, we can put 2 electrons. So there's lithium's first 2 electrons. And then in our second shell, lithium has only 1. Shorthand way for Bohr models. Once you get really good at drawing Bohr models, you can shorthand them so that they look like that. This represents the first shell, and in the first shell there are 2 electrons, and this represents the second shell, and in the second shell there's only 1. Now, like I said, I much prefer Lewis structures myself. Another guy comes along, he says, listen dude, the only thing that is really important to us is the electrons that are in that outermost shell, called valence electrons. And if those valence electrons are the only thing that's really important to us, then why not just draw the valence electrons? So for example, if we took a look at chlorine, chlorine's too big. Let's look at fluorine. If we take a look at fluorine, fluorine would have 2 in the first and 7 in its second shell, having 7 valence electrons. Therefore, the Lewis structure for fluorine would look like that. I don't know about you, but I'd much rather draw this than circles with numbers and try to figure out what I really mean there. Okay? Just a quick review of how we actually draw or represent those electrons in those orbitals around our atoms. Okay. This is a question that kind of comes up, and I've mentioned or kind of alluded to talking about this before. And it did come up with a couple of the classes who we've already done these notes with. When is it possible that the number of protons of an atom could be changed? And the only time that it is possible that you have the number of protons change is in what's called a nuclear decay reaction. So we're typically starting a nuclear decay reaction with a radioactive isotope to begin with. Okay, and these are just examples of different ones. Okay, so you can see here, for example, we started off with carbon. Okay, this one didn't happen to be carbon radioactive. When we have the nuclear decay happening, we actually add a proton to this particular element, and we end up with nitrogen instead of carbon. Okay, sometimes you'll change and you'll lose them. Okay, one of the most common nuclear ones that happen in nuclear reactors all the time is going from uranium to thorium. And if you take a look at what happens there on your periodic table, we go from uranium to thorium. Uranium is 92, I think. Don't hold me. I don't have a periodic table in front of me. Down to thorium, which is 90. So essentially, your uranium lost 2 electrons in the nuclear decay. It's the only time you can change the number of protons and actually change the element. Okay, a couple of last things to do here. Hopefully it won't take us too much longer to do this. I want to just make sure that we know the difference between chemicals that are compounds and chemicals that are molecules. I want to make a little chart down here. I'm going to move this up a little bit so that we can see better. Compounds versus molecules. Compounds, you're typically looking at 2 atoms. They're usually simply bonded. Most of the time ionic, sometimes covalent. Molecules, on the other hand, you'll have greater than 3, 4, 5, all the way to the hundreds of atoms involved, as you can see from over here. This is the molecule or the molecular diagram of caffeine. Maybe after me talking for this long, you're all in need of a little caffeine. And not only are they going to be covalently bonded the majority of the time, but you're going to have a whole host of other types of bonds happening. You'll also have hydrogen bonds. We'll have things called van der Waals forces. Some other different types of bonds, peptide bonds. We'll get to that in the next chapter. And just, you know, they just can be, that's how they can become these huge molecules with all these hundreds of different atoms because of all the different types of bonds that are in there. Okay, so before we leave this one, I want to make sure you understand what this guy is over here, so that you're not looking at him being some kind of weird, slightly not appropriate acronym for something. This guy right here, I'm going to pull out, and we're going to talk about him up here. This is a diatomic molecule, or this is a listing of diatomic molecules. These are molecules. Oh my goodness, you can't see. That's better. These are molecules that exist naturally, bonded to themselves. So what you're really looking at is a series of the symbols of the diatomic molecules. So this is boron, iodine, chlorine, hydrogen, fluorine, oxygen, and nitrogen. These all exist bonded to themselves. So you would have B2, I2, Cl2, H2, F2, O2, and N2. And it's important to understand that these molecules exist because when you're trying to figure out what the reactants could possibly be that would give you two products, or what the products are going to be from the reactants in a reaction, or you're trying to balance an equation and all you were given were the words for the equation, then you kind of need to remember that these guys exist like this. When you're saying that oxygen is involved in a reaction, you need to remember that it's O2 and not just O. So it's important for being able to balance chemical equations that you know that these guys actually exist. Okay, you're going to have practice for all of the stuff that I've talked about so far, and you're also going to have practice for the two main types of bonding, which are ionic and covalent. So there are some keys to understanding ionic bonding versus covalent bonding, and once you get them down, and you pretty much have to memorize them, although I know nowadays we can Google anything, right? Ionic bond key points to ionic bonding. One is always between a metal and a nonmetal. Two, metal is going to give up the electrons, and the nonmetal is going to take them on. And the last thing is you're not going to get neutral atoms back. So when they break, and we kind of alluded to this before when we were talking about ions, when an ionic bond breaks, you get ions as the result, not neutral atoms. So taking a real quick look, because I think this is probably review for most of you, this is the sodium atom over here. Notice it has one electron in its outermost shell. The shell underneath is full. That's what makes sodium ready to give up this outermost electron so that its outermost shell could be full. Chlorine over here has 7 electrons in its outermost shell. Therefore, if it could fill this one last spot, chlorine would be a much happier camper. And so that's why this bond between sodium and chlorine, making sodium chloride, also known as table salt, happens. If I dissociate or break this bond, these bonds in any way, I'm not going to get my original sodium back. He gave up his electron. So therefore, if I was to break this bond, I could have drawn that breaking better, I would end up with sodium ion and chlorine ion as the result. Okay, real quick, let's do covalent bonding. The difference between an ionic bond and a covalent bond is in covalent bonds, the atoms are sharing electrons. I'm sure this is nothing new. You've all done this before. We're usually not talking about metals. Covalent bonds happen pretty much most of the time between all non-metals. That's supposed to say non-metals. And the reason they share electrons is to fill the outer shells. So our examples here are hydrogen. These are both diatomic molecules, hydrogen and oxygen, just like we saw on the previous page or two. And then we have water down here at the bottom. Water gets a little bit tricky in its covalent bond. We're going to give water some special attention in a day or two. But let's focus on these two here for now. So both hydrogen atoms have only one electron in their outermost shell. And to fill their outermost shell, remember that first shell can only have 2 electrons. Therefore, let's say this hydrogen electron belongs to him originally. This electron is going to spend time around this and then around this and then around this one. And I'm sure I could go on and on and on and on forever. And you'd figure out that some of the time that hydrogen electron is spending time around the hydrogen that it belonged to, but it's also spending time around this hydrogen as well. That's how both of those atoms feel that their outer electron shell is full. Same thing's going to happen down here with oxygen, but as you can see, there's 1, 2, 3, 4 electrons that are being shared between those 2 oxygen atoms. 2 belong to this oxygen and 2 belong to this oxygen. And so some of the times this oxygen will have 8 in its outermost shell, and some of the times this oxygen will have 8 in its shells. Notice that because we're sharing 2 sets of electrons, or 4 electrons total, we have a double bond. That occurs between those 2 oxygen atoms. Down here, real quickly, just so you can see what's going on, this one's hydrogens, this one's oxygens. Sometimes his is spinning around him, sometimes oxygen is spinning around hydrogen, and then vice versa. Sometimes hydrogen is spinning around the oxygen, and sometimes the oxygen is spinning around there. Okay, that's essentially what you need to cover for today. The remainder of the time, the substitute's going to hand to you the worksheet packets and tell you when they're due. Don't worry about getting them completed. Do your best. I know I wasn't there to immediately address any of your questions, so let's see how far you can get. Feel free to use other resources, your textbook, online, whatever you need to, and we'll go over them when I get back. All right, guys, have a good day.